Everyone. Got a little break in the weather here, so I think the heat's behind us for a while. Today we're going to finish up talking about lines and planes. So we'll finish talking about lines, and then we'll talk about planes. So yesterday we talked about sort of three different forms of a line. We've got the vector form, we've got the parametric form, and the symmetric form. So just a quick review here. The way we can think about creating a line is we can start with a point on the line, and we can start with a vector, which gives us a direction for the line. And then what we do to trace out the line is we look at, from a vector point of view, we start at the origin, and we go up to the point P, and then we trace out scalar multiples of the vector V, and that's going to get us to other points on the line. Okay, so think of this as where we start plus a scalar multiple of the direction. So if we write that out in a generic form, if we've got a point x naught, y naught, z naught, and we want to be parallel to the line ABC, then we look component by component. We're starting at some value x naught, and for each increment of t, we're moving a units in the t direction, and then analogously for y and z. So remember, when you think of a vector, you can think of this as delta x, delta y, delta z. So think of this as your starting point plus your change in whatever direction times t. Now the parametric form, or the parametric description of the line, is just calling out the x, y, and z components. And if we solve each of these equations for the parameter t and set the results equal to each other, thereby eliminating the parameter, we get the symmetric form of the line. So we did some examples yesterday. We talked about how you can graph these on GeoGebra to check answers and whatnot. And we did a little bit looking at intersecting lines. And really the point is that there are infinitely many representations for the exact same line. Distance from a point to a line. We derived this formula yesterday. We got example 4 set up, but we didn't actually do the calculation. Was there any issues here actually getting the distance to work out once we went through your P, Q, V, and all that good stuff? So make sure you get that. Walk through the process. So which part of it? Because we did the PQ. So first thing is you got to find a point P on the line. So what's the easiest one? So this L of t gives you all the points on the line. So what's the easiest value of L to plug in to get a point on the line? So plug 0 in. That's going to give us 0, negative 3, 1. So that's going to correspond to our point P. Okay. So now we need to look at the vector from P to Q. So they give us Q is the point 0, 1, negative 3. So we would create the vector from P to Q. So we end at Q and start at P. So we always take the final minus the initial. 0 minus 0 is 0. 1 minus negative 3 is 4. Negative 3 minus 1 is negative 4. So we good with getting the vector P to Q? We okay with the vector from P to Q? Now we need the vector V. We need a vector that's parallel to the line. And so remember, to get the vector parallel to the line, you look at the coefficients of t. That'll give you a vector parallel to the line. So we've got 2t here, so that coefficient is 2. We've got t here, which means the coefficient's what? So what's the coefficient of t in this component? 1. And then 3t here, coefficient's 3, so that's our v. So then to get the distance, what you would need to do is you need to look at, well, here's the formula here. So the distance is the magnitude of PQ cross V over the magnitude of V. So you'd have to find your PQ cross V, so that's the cross product that we talked about on Tuesday. And then you calculate the magnitude of that, like we talked about last week. And then you'd have to get the magnitude of V. And then you would just divide this answer by that answer. Okay? And it doesn't matter what point you pick for P. It'll all come out in the wash. So you could plug in like 1, -1. You could plug in 11d7 if you wanted for T. Doesn't matter what point you pick. This will always give you the correct distance. Okay? Is that a good enough walkthrough there for you, Abby? All right. Let's talk about parallel and skew lines. So yesterday we did an example where we had two different representations for the same line, and we saw what happened there algebraically. Let's talk about parallel and skew lines. So when you have two lines, either in the plane or in space, you've got a couple different scenarios. You could in fact have the exact same line. So we saw what happens yesterday. You set the components equal to each other, and then you end up getting a infinitely many intersection points. So that would give you the same line. So in other words, if they intersect more than once, they intersect everywhere and it's the same line. You could have two lines that intersect only once. Okay. You could have two lines that don't intersect. So this is where things get a little different in 3 space. So these are the cases for intersecting lines. You either get one intersection or you get all the intersections. All right. If they're not intersecting, well, they could be what? So you have this in 2 space. If you have two non-intersecting lines, they are what? Yeah, they could be parallel. Or in 3 space, I mean, you could have parallel lines. In 3 space, they could be what are called skew, which means they lie in different planes. So they're not parallel, but they also don't intersect. So that's something we get in 3 space that you don't get in 2 space. Does that make sense or not? So then the question is, how do we detect these things? So we can show that they're, so what we do is this, is we equate components. That's going to give us a system of equation. If there's only one solution, then it's one intersection. If there's infinitely many solutions like we had yesterday, that means it's going to be the same line. If there's no solutions, then we have two cases. If you've got the same or opposite direction, then we've got parallel lines. If not parallel, then we have skew. All right? So we've seen an example of this already. Work the following problems algebraically and check graphically. Show the lines L1 and L2 are parallel. Okay, so if I want to show lines are parallel, I got to show two things. I have to show that they don't intersect, and I have to show they have the same or opposite direction. So to look to see about intersection, I equate corresponding components and solve the system. So if I'm looking for intersection points, the x coordinate on the first line would have to be the x coordinate on the second line. So there has to be a value of t on where 2t plus 1 is equal to a value for s, 1 minus 4s. The y coordinates would have to be the same. And the z coordinates would have to be the same. All right? Do you see why we're equating the x's, y's, and z's? Because we're looking for a point on both lines, so the x, y's, and z's have to be the same. So we have a system of equations here. We have three equations with two unknowns. So in the business, this is called an overdetermined system. Okay, so anything's possible here. So we just kind of go through and solve, substitution, elimination, however you were taught to do it. If we look down here at z, one way to start is we could solve this for s. S is 2 minus t over 2. And then we can substitute this in to these two equations. And then get an equation for t and see what happens. So if I look at my equation for x, I have 2t plus 1 is 1 minus 4s. But for s, I'm going to substitute in 2 minus t over 2. And let's work this out. I'd have 2t plus 1 equals 1 minus, and I've got, let's see, I can simplify, and I'm going to distribute the negative 2. So be careful here. The negative 2 times the 2 is a minus 4, but the negative 2 times the negative t is going to be a positive 2t. And look what happens. What happens to the two t's, folks? When I try to solve, what do I get? Yeah, cancel out. So I get 1 equals negative 3, and that's no good. There's no solution. Now, what does that mean? That means that if you try to have a value of t where 2t plus 1, 3 minus t, and 2t, in other words, where the x, y, and z on the first line matches the x, y, and z on the second line for a single value of s, there's no value of t that's going to generate the same point as a single value of s. That means that there's no points in common. So this means that L1 and L2 do not intersect. You follow the logic there or not, folks? So if you try to get a t and an s so that the x, y's, and z's all match up at the same place, you just can't happen. You get nonsense from that. Okay? So the L1 and L2 do not intersect. That's the first thing. So at this point, either the lines, they're either skew or parallel. To determine which is which, we have to look at the direction. So for L1, I need a vector that's parallel to L1. And once again, we get those by looking at the coefficients of t. So we have a coefficient there. We've got 2t in the x, 3t for the y, and minus t for the z. So the coefficient of x is 2. The coefficient of y is 3. And what's the coefficient of t here in the z component? What's the coefficient of t in the z component? It's 2 minus t, so it's what? -1. Good. All right. So that's a vector parallel to L1. Let's get a vector parallel to L2. Let's call that V1. Here's a vector parallel to L2. You go through the same thing, but you look at the coefficients of s. So we got a -4s, -6s, 2s. So -4, -6, 2. And if I want to show that these vectors are parallel, so I need to know, I need to look to see is V1 parallel to V2. I need to see if they have, if one is a scalar multiple of each other. So the easiest way to do this, I think, is to just start dividing the corresponding components. So let's take the x components here. I take -4 over 2. That gets me that's a -2. Is that the same ratio with the y's and the z's? So we have the same ratio all throughout. So this tells us that V2 rather, is just -2 V1, which proves that they're parallel. Okay? So since the direction vectors for the lines are parallel and the lines don't intersect, that means that the lines L1 and L2 are parallel. So to put it all together, since L1 and L2 do not intersect, and L1 and L2 have parallel direction vectors, L1 and L2 are parallel. Okay? Make sense or not, folks? Show the lines L1 and L2 are identical. We did one like this yesterday. What you would do to get started is, once again, you'd set the components equal to each other. 2t plus 1 is 3 minus 2s. 3t is 3 minus 3s. 2 minus t is s plus 1. And you would end up getting one equation. So you get, something s equals something t. And then when you plug that in, you would get two equations that were identities. All right? So we did one like this yesterday. I transposed something. We had to go back and fix it. But so in other words, you would get infinitely many answers. That's how you know that they're identical. Find where L1 and L2 intersect. So you would start off doing the same thing. So you'd have 2t plus 1 is 3 minus s. 3t is minus s. And then 2 minus t is s minus 2. And then if you go through this equation, you'll get exactly one answer. You'll get an answer for t. You'll get an answer for s. And when you plug your answer in for t to x, y, and z, you'll get this point out. And that'll be the same point you get when you plug in your answer for s. So once again, you just go through and solve that system of equations using substitution elimination. You see why we're equating the components though, folks? Does that concept make sense? That's the big concept there. And then last but not least, show these lines are skew. So to show lines are skew, you first got to show that they do not intersect. So in other words, you would set up that system and you'd get no solution. So you'd get something like 0 equals 1 or something. And then you'd have to show that the vectors are not parallel. So I'll leave the algebra to you, since we've already done a couple of these here over the past couple of days. But let's show how the vectors are not parallel. You have to show the vectors are not scalar multiples of each other. So we'll do that part of it. So let's get a vector v1 for L1 and a vector v2 for L2. And remember, the way you can get these parallel vectors is to read off the coefficients of the parameters. So v1, I've got 2t, 3t minus t. So this is the same v1 we had before, 2, 3, negative 1. And what would be the vector v2 for L2? So what's a vector that's parallel to L2? Yep, very good. We got 1s, 2s, 1s. So 1, 2, 1. Now to show that v1, we're looking at v1 parallel to v2, well, let's look at the ratio of components. If I look at the x components here, if I look at, I've got a 2/1 ratio. The y components, I've got a 3/2 ratio, and these are not the same. So I don't have a common ratio throughout the components, and therefore the vectors are not parallel. So that would mean that the lines are skew. All right. Now we can check this once again. Just fire up GeoGebra here. Remember how you can enter lines, because this will be helpful when you go through your homework and take home here. You just enter them 2t plus 1, 3t. You just enter them as parametrics. You enter them as just coordinates there. And if you want, you can switch the s, but I'll just convert all the s's to t's, because sometimes GeoGebra will parse that as a new parameter. Sometimes it won't. But the safe bet is to just go back to t's. And here's the two lines. And I think you can see that they're clearly not parallel, but also they do not intersect. Right. So you can ask yourself, how would you find the distance between L1 and L2? You can think about geometrically what you would do. To see if you can kind of put some of these pieces together. All right, let's talk about the equation of a plane. Now you may remember back to geometry We can determine a plane in geometry how? Normally you need what to determine a plane? Yeah, 3 points. Okay, that'll determine a plane as long as those 3 points are non-collinear. In other words, you need to have 3 points that don't end up being on a line. Well, with vectors, we're going to have a sort of a different way to approach this, and we'll be able to get back to the 3-point approach. But this is what we do. What we're going to do is we're going to pick a point P on the plane. We're going to give that the coordinates x naught, y naught, z naught. And we're going to pick a vector n called a normal vector. Normal meaning that it's going to hit the plane at a 90-degree angle. So in other words, it's orthogonal to the plane. So I think my email's up. Hold on here. Let's shut that down. So let's say we've got a point Q that's on the plane. Then the way Q is going to be on the plane is if n is orthogonal to the vector PQ. And we can check if two vectors are orthogonal by calculating their what? Dot product. So if n has components a, b, c, the vector from P to Q would be x minus x naught, y minus y naught, z minus z naught. That has to be 0. And so we get these. We get this formulation for the equation of the plane, which sort of reminds us of where it's coming from with the dot product. Or you can simplify it to get this one. Just pick whichever one floats your boat. But let's do a quick example here to make sure we understand how these formulas work. Find the equation of the plane containing the point P, 1, 2, negative 2, 3, and the normal vector 3, negative 1, 2. So we got x naught, y naught, z naught there. That's our particular point. The n, these are the directions, A, B, C. And just like with lines, notice, you see what's happening here? The components of the vector are the coefficients of the variables. So I'm going to start with the x component 3 times x minus the x coordinate 1 plus the y component negative 1 times y minus the y coordinate, negative 2. Plus the z component negative 2 times z minus the z coordinate 3. And this is the most common mistake. Don't forget this is all equal to 0, which I'm gonna recopy this because I ran out of room there. But you got the x component times x minus the x coordinate plus the y component times y minus the y coordinate plus the z component times z minus the z coordinate. Don't forget, if you're using that formula, that's equal to 0. A lot of folks just leave that hanging. But we can go through and work this out. Distribute. And folks, please, when you're writing this out, have some clear way to indicate if something's a 2 or something's a z, if something's an s or something's a 5. I tend to put lines through the middle of my z's because sometimes my 2 has loops, sometimes they don't. Then you can gather everything up. You can got 3x minus y minus 2z. You got a minus 3 minus 2 plus 6, and you get to that. And once again, you can fire up GeoGebra to help you check. But are there any questions on feeding the information into the formula? You see where all the stuff's coming from? So let's check this on GeoGebra. So we'll type in our plane. Oops. We'll just type in what we got there. The 3x minus y minus 2z is negative 1. And we'll fire up the point P, 1, negative 2, 3. And we'll look at the normal vector, we'll call it n. And we'll put it in standard position, and then we'll translate it. 3, negative 1, negative 2. So that would be the normal vector. Oops. Oh, actually, you can kind of see it's normal. There, it's at a 90 degree with the plane. We could actually move it over to P if we wanted to. We can go to our tools, and then we can do we did this yesterday. There's a vector from point, transform, vector from a point. Select the starting point in the vector, so we'll select our point P and select our vector n. There it is. And I think you can see there, oops, you can see how that vector there is orthogonal to the plane. Okay. Now let's get back to what Abby mentioned. Back in geometry, you can get a plane if you have 3 non-collinear points. So let's just think about how we can do this, and then I'll leave the details of this to you, and then you can check it on GeoGebra here. But let's say you've got 3 non-collinear points, P, Q, and R, and you want to determine a plane. Well, for us, we need a point P, and we need a normal vector n. Normal meaning, once again, orthogonal to the plane. So what we can do is we can construct n from these points, because I could find the vector from P to Q, and then I could find the vector from P to R, and then think back to earlier this week. What vector could I calculate that will get me a vector that's orthogonal to both PQ and PR? The cross product. Perfect. So I would take PQ cross PR, and that would be my vector n. So remember, the cross product is going to give you a vector that follows the right-hand rule that's orthogonal to both. So you would have your vector P, you'd go through the cross product to get your vector n, and then you would go in and use the recipe that we did on example 6, and that would get you the answer. Okay? So once again, we can get to the same results we had before. If you remember trying to figure out the equation of a plane with 3 points, that could be a little challenging. There's a lot of algebra there. This one kind of takes a lot of that away using vectors. So we have better tools to attack the same problems. All right, let's think about how we would find the distance between a point and a plane. Yesterday, we talked about how to get the distance between a point and a line. So let's look at the distance between a point and a plane. So let's say we've got a point, the same setup we had before. So we got our normal vector n and point P sitting on there, okay? And let's say we've got some point Q that's up here that is not on the plane. what we want to do is we want to figure out what the distance is to the plane. And just like when we were looking between the distance from a point and a line, the distance here is going to be the length of this line segment, and this line segment is going to intersect at a 90-degree angle. That'll be the shortest distance that we have. So what can we do? Well, there are a couple different ways to think about it. We could set up a little right triangle and do what we did yesterday, or we can make use of the dot products. So here's what, since that's 90 degrees and we have the normal direction already, here's what we need to do is I can construct the vector from P to Q, and then I can project that vector onto the normal vector. So I can just copy and paste the normal vector here. And if I project PQ onto N and take the length of that, then I'm good to go. So the distance I want would be the magnitude of the projection of PQ onto N. So before we go any further with that, do you understand the geometry of what's going on there? Remember, projection is we basically taking the shadow. So we're going to project PQ, going to project that onto the normal vector, and then measure the length of that. So let me know if that procedure makes sense. All right, well, let's do it then. So we go back to what we learned last week. The projection of PQ onto N is PQ dot N over the magnitude of N squared times N. And remember that PQ dot N is a real number. The magnitude squared is a real number. So this is all a real number, which I can factor out of the length. Now, when you factor it out of the length, it's going to come out as a positive number because lengths are always positive. Now, the magnitude of N squared, that's always positive. But this may not be positive. So we'd have to make absolute values there. And then I'd have the length of N. And look what happens. We get a little cancellation here. And I get the magnitude of PQ, or excuse me, the absolute value of PQ dot N over the magnitude of N, and that's our distance. If you want, you can float this scalar in through the absolute value and into N to get this prettier formula. You're looking at literally how much of PQ is in N's direction, and then taking the absolute value of that. That's literally the whole concept behind dot product. Anyhow, we get this. Okay. So let's find the distance from the origin to the plane. X plus 2y plus 3z is 6. So to do this, first off, the origin, can you see why the origin is not on the plane? Because what are the coordinates of the origin? Yeah, 0, 0, 0. So you see why the origin isn't on the plane? Because if you let x, y, and z all be 0, you get 0 equals 6. You follow? So that equation isn't true. So the way you can show a point is or is not on an equation is plug in the x, y, z coordinates and see if the equation is true. It's definitely not true. So this is the point that's not on the plane. So that's going to be like what we were calling Q. Now I need to come up with a point that is on the plane. So what's a quick way to figure out a point on this plane? 0, 0, 0 isn't on it, but 0, 0 what would be? Good. 2. Whoops. Not 0, 2. So a quick way to find a point on the plane is to zero out 2 of the coordinates. And we'll talk more about this tomorrow when we're talking about graphing surfaces. So if I look at the vector from P to Q, then, well, that's 0, 0, 2. So that's my vector from P to Q. Now I need a normal vector n. Just like with lines, the parallel vector with lines can be read off looking at the coefficients of the variable. N is the same way. So if I look at n and I want the x component of the normal vector, I look at the coefficient of x, which is 1. Coefficient of y, and the coefficient of z. Any questions on how we figured out who was q, how we got a p, the vector pq, and the vector n? Do you see where we're getting all the ingredients for this? So now I just fire up the formula. I take n dot pq, and how do we get the dot product of two vectors? We multiply the corresponding components. Yes, thank you. I went the wrong way. Thank you. Thank you. All right, so yeah, PQ is 0, 0, negative 2, because we're starting at P and going to Q. So we multiply the corresponding components, and we add them up. Now, the nice thing here is that the x's and y's completely cancel out. I just get negative 6. And now I find the magnitude of the normal vector. And so when we think of the length of the normal vector, the magnitude of the normal vector, we think to our friend the distance formula, aka Pythagorean theorem. So how do we find the magnitude of a vector? We square the components, add them up, take the square root. And so the magnitude of n, I get the square root of what? $14. Good. So my distance then would be the absolute value of n dot pq over the magnitude of n. So that would be a positive 6 over root 14 units, whatever the units of distance are. Okay. Now, something that's worth noting is when you had a line with a parallel vector v, and you had a point that wasn't on the line and a point that was on the line, the distance here was the magnitude of PQ cross V. This is what we just reviewed at the beginning of class here, thanks to Abby's question, over the length of V, which you could write more succinctly as PQ cross, the length of PQ cross V hat. Here, if we've got a vector or a point P, a normal vector n, and a point Q that's not on the plane, the distance was the absolute value of PQ dot n over the magnitude of n, which is the absolute value of PQ dot n hat. So lines are determined by parallel. The cross product detects parallel. So if the point Q were actually on the line L, these two would be parallel vectors and we would get a distance of 0. So we're kind of measuring there that distance using the length of the cross product with a direction vector. Here, if Q were on the plane, then P, Q, and N would be orthogonal and the distance would be 0. So this is measuring then how far away we are from being orthogonal. The vector PQ is being orthogonal to the vector N. So there's a nice duality set up here between parallel definition of lines and the perpendicular definition of planes. There's that duality here. So I would be remiss if I did not point that out. It's a beautiful little thing. All right, let's talk about planes. So now you got two big planes sitting here in 3 space. They could either not intersect at all, and the only way that would happen is if they were parallel planes. Parallel planes, what would be parallel? If I had a vector n1 and a vector n2, parallel planes would have parallel vectors. They would be non-intersecting, so there'd be no intersections, and then the normal vectors would be parallel. If they do intersect and they're not the same plane, then you can imagine, two sheets of paper kind of cutting across each other. They would intersect on a line. So find a representation of the line of intersection of these planes. So once again, in order to be a point on the first plane, x plus 2y plus 3z would have to be 6. To be on the second plane, 3x plus 2y plus z has to be 12. So this is a system of 2 equations with 3 unknowns. This is called an underdetermined system. When we have the system of equations for lines, those are overdetermined because we have two variables and 3 unknowns, or excuse me, 2 variables and 3 equations. Here we've got 3 variables and 2 equations. So your best bet is to do a little substitution. So if I take that first equation here, I can solve that for x. And then I can plug that into the second equation. And this will give me a relationship between y and z. So if I distribute that 3 through, I would get my 18 minus 6y minus 9z plus 2y plus z is 12. And now what we can do here is solve for either y or z in terms of the other variable. So if we got, let's see, minus 6y plus 2y, so minus 4y, minus 8z would equal, well, let's see, we'd have the 12 minus 18, negative 6. So if I wanted to, I could solve this equation for y. I'd be adding the 8z over and then dividing by 4, negative 4 rather. So that would be what? Negative 2z plus 3 halves. And so z would be a free variable. Z could be anything you want it to be. So this is where the parameter comes in for the line. So we would say, okay, let's let z be t Then for y, I can just plug z in to this equation. I'm just double checking that I didn't transpose something incorrectly. I think we're good on this. So z would be t. Y then would be minus 2t plus 3 halves. And then what would x be? Well, I'd go back. X is equal to 6 minus 2y minus 3z. 6 minus 2y. And if your bell's rung, I know you have to go. That's fine. Minus 3t. But I'll finish this off, and you can always fire up the video if you want to see the check here. So that would be a minus, would be a minus, a minus would be a plus 4t. Minus 3, minus 3t. So I would get a t plus a 3 would be my x. So that would be my x component, my y component, my z component. And let's see if that matches what we've got here, because there's infinitely different ways to do it. Yep, so that works. So that matches the same representation I have here. So let's talk about how we would check this. One way to check this is to plug x equals t plus 3, y equal minus 2t plus 3 halves, and z equals t. Plug these into each of the original equations. So plug those into here and show that regardless of t, if you add those things up, you get 6. And if you add these things up, you get 12. Or what you could do is fire up GeoGebra, graph this plane, graph that plane, and graph that line, and you'll see the intersection. Okay. Showing planes are parallel, very similar to how we show lines are parallel. You would go through the algebra and show that there's no intersection points. So you're going to get like a 0 equals 1 situation here. And then 2, you want to show that, well, if there's no intersection points, they're forced to be parallel. Okay. So you don't need to, but then you can just show that the normal vectors are in fact parallel as well.